Hello everyone, my name is JMeyers, and today we are going to be going over the power management system for our first knowledge integration. I'm in all of the electrical engineering courses. All the information gathered from those can tell us how the AC input signal here becomes a DC output signal here. First, we're looking at this sinusoidal voltage going through this diode bridge in our rectifier. Now, rectifiers are a nonlinear time invariant based system. The diodes are nonlinear in and of itself, and time invariance is something that we're wanting very badly because we are going to be having the input signal become purely a positive waveform. After this diode bridge, we're going to see how the polarization of this flips and sends purely a positive waveform signal through into the output of the rectifier, as we can see here. The AC input signal at this point here is where the polarity switches on the input signal so that we have a positive signal going constantly and sending a positive output to the rectifier output. As always, we can see how these coincide with each side of everything. So we have a flip to the negative cycle here and then back to the positive cycle, but we're seeing purely positive, and this is the resultant output of the rectifier. We can see that this is the actual output of the rectifier. This is our ideal input signal, and this is our constant voltage output signal. Now, the discrepancy between these two is because of the threshold voltage that occurs over the two diodes that we will be constantly passing through during these switching cycles. And we can additionally see here that there's some loss in energy between them. This can be attributable to heat more so than anything else, but we can continue on to see why we are needing these voltage thresholds and why they occur. Now, the threshold is due to the required energy in order to eradicate this depletion barrier and the potential barrier to break it through so that we can send current throughout it. Now, here's the depletion barrier, and we have our positive and negative, or our P region and our N region here, and we have an electric field going across here. Here we can see that the junction region, the depletion region, has no free charge carriers, I should say, and the depletion region has a actual physical thickness, and we can actually determine the width of this. Electrostatic analysis, we can find charge and field in the depletion region, the electric field. And we can, by integrating, deduce the electric field density, proving that the diode is on, and we can prove how large the junction is distance-wise, which allows us to understand the voltage threshold and what we can see, and we know that the forward biased PN junction allows current through, and our reverse biased does not allow this, and this is because an effective resistance comes about across here due to a positive voltage coming in through the N side, pushing all these positive holes over into the depletion region and creating this larger thickness and completely depriving current from traveling through. And we can see how the actual bridge itself works. We follow the output through forward bias, taking us through the load, all of that, and then we can see how, once the threshold voltage is no longer sufficient for D1 and D2, we can see how it flips at that 0 point, which is here, and being able for it to clear over to these diodes in order for a constant output of constant positive output. Now we're going to move on to the RC circuit and see why we need this capacitor, and we're needing it because we need to establish a relationship between our charge and our voltage. Now we're going to look and see how the RC circuit is a linear-based circuit that we are needing time invariance with as well, because again we are wanting our input and output to reflect each other based on changes in the input. And it is linear as well. We are wanting the waveforms, even additionally speaking, to hop on top of each other in any form of scalar quantity or anything along those lines. And so with the output current from the rectifier, we're able to apply the capacitance of the RC circuit over this to create a ripple effect. Here we see that there is constant voltage, and this is 2VD on, the point in which there is no current going through the diode, and I ends up going to 0. It will be at about this point, extending over. We'll be able to see this in the next graph here. And we can see that the capacitor discharges at this point and charges as well. And the capacitor acts as a smoothing capacitor. So the greater the capacitor, the more smooth it will become and will end up going into a purely DC-based output, which is exactly what we're wanting. So there will be less ripple associated with this. Due to conservation of energy, when the ripples become less and less, we will be able to see that the discharge time is less, and the electric field, when the capacitor is discharging between the plates of the diode, is storing more and retaining more energy. And the more it retains, the more it becomes a straight line. So that is about all the time that I have allotted. So thank you very much, and I will see you later.